Hey everyone, and welcome. Today, we're going to pull back the curtain on a really cool type of AI called a restricted Boltzmann machine and figure out how it actually learns. And don't worry, we're going to ditch the dense math for now. Instead, we're starting with a little neighborhood mystery. Okay, so let's dive right in. Picture this. You're watching a house across the street, and every day, three people show up to visit. Their names are Aisha, Beto, and Cameron. But after just a few days, you realize something is, well, kind of weird about their schedule. Day in and day out, you only ever see two patterns. Either Aisha and Cameron show up together at the same time, or Beto shows up completely by himself. That's it. No other combinations, ever. Now, the obvious assumption is that they've got some kind of coordinated schedule, right? But here's the kicker. You find out they don't even know each other. So what on earth is going on here? Well, the solution has nothing to do with the people you can see. It's all about two residents of the house that you can't see. See, living inside are a dog named Descartes and a cat named Euler. And it turns out, Aisha and Cameron are huge dog lovers, but they can't stand cats. Meanwhile, Beto absolutely adores cats, but is terribly allergic to dogs. And boom, just like that, the whole strange pattern makes perfect sense. And believe it or not, this little neighborhood mystery is a perfect analogy for how a restricted Boltzmann machine, or RBM for short, actually works. The people we can see, Aisha, Beto, and Cameron, that's our visible layer. It's just the raw data we have access to. But the pets, the ones we had to figure out to make sense of everything, that's the hidden layer. They are the secret, unobserved features that are really driving the whole pattern. So here's how it all maps out, nice and simple. The connections between the visible and hidden layers, like Aisha's love for dogs or Beto's cat allergy, those are called weights in an RBM. A big positive weight means a strong positive connection. A negative weight? Well, that means a negative one, kind of like an allergy. An RBM basically assigns a score to every single possible scenario. You can think of this score like an energy level. A really stable, likely situation gets a high score. So a scenario where Aisha, Cameron, and Descartes the dog are all there. We add up all those positive weights, and that combination gets a really high score. On the other hand, a scenario with Beto and the dog gets a super low score. The rule is simple. The higher the score, the more likely the scenario. Okay, so here is the million-dollar question. We figured out the mystery with our human brains. But how does a machine, starting from a total blank slate, let's say all the weights are just zero, how does it learn these hidden relationships just by looking at the visitor log? How does it figure out who likes which path? Well, that's exactly what the training process is for. The entire goal is to just keep adjusting those weights, those connections between people and pets, over and over again. We want to keep nudging them little by little until the model's own internal idea of what's likely perfectly matches the real-world data we've been observing. Now, your first thought might be, well, why don't we just calculate the score for every single possible combination of people and pets and work backwards from there? And, for our tiny little example, you probably could. But what happens when we scale this up to a real problem? Get ready for this number. For even a pretty modest RBM, maybe with 200 visible units and 100 hidden ones, you're looking at 2 to the power of 300 possible states. That number it's so mind-bogglingly huge, it's basically meaningless. It's more than the estimated number of atoms in the entire known universe. So yeah, calculating everything is completely, totally off the table. So we clearly can't just brute force our way through this. We need a shortcut. We need a clever hack that lets us get to the right answer without doing an impossible amount of work. And luckily for us, one exists. It's an algorithm called Contrastive Divergence. Let's break down how this hack works step by step. It's actually a pretty elegant loop. First, you start with a real piece of data. We call this the positive phase. Then, you use that data to make a guess about the hidden layer. Third, you use that hidden guess to dream up what the visible data should look like. That's the negative phase. And finally, you just nudge the weights to make your model a little more like reality and a little less like its own dream. Let's walk through it. Okay, step 1, the positive phase. We grab a real data point from our log. Aisha and Cameron showed up. Now, we have to figure out the probability of each pet being present. And here is the magic of why RBMs are restricted. Because the hidden units, the pets, aren't connected to each other, we can calculate the probability for Descartes without worrying at all about what Euler is doing. They're independent. This is a huge deal, and it simplifies the math tremendously. So how do we get from one of those scores to an actual probability? For that, we use a handy little mathematical tool called the sigmoid function. All this thing really does is take any number you give it, big, small, positive, negative, and it just squishes it down into a nice, neat value between 0 and 1, which is, you guessed it, a probability. High scores get close to 1, low scores get close to 0. Simple as that. Let's see this in action. To find the probability of Descartes the dog being there, we add up all the relevant scores, his own base score, plus the connection weights from Alicia and from Cameron. Let's imagine for now that sum equals 1.L. We pop that 1.L into our sigmoid function, and out comes 0.73. That's it. Based on the current weights, our model thinks there's a 73% chance the dog is present. All right, now for the fun part, the negative phase. We take that 73% probability, and we basically flip a weighted coin. Let's say it lands on yes, Descartes is present. Now we work backward. We go to the model and we ask, okay, based only on the dog being here, who do you think should be visiting? This reconstruction is the RBM's dream. It's the model's own fantasy of what reality should look like based on what it knows so far. And this brings us to the most important step, the learning. We compare reality to the dream. We look at the connections that were active in the real data, the positive phase, and we nudge those weights up just a tiny bit, strengthening them. Then we look at the connections that were active in the model's dream, the negative phase, and we nudge those weights down. In short, we reinforce reality and we discourage the fantasy. This whole back and forth process, going from visible to hidden and back again, is one step of something called Gibbs sampling. In practice, we might even repeat this little loop a few times. It's like taking a short, random walk away from our real data point. We don't need to see the entire map of all possibilities. We just need to take a few steps to get a good sample of what the model currently believes. Now, you do this simple update process thousands and thousands of times for every data point you have. And slowly but surely, the weights start to adjust. The model learns to make the connections stronger between Aisha, Cameron, and the dog, and between Beto and the cat. And eventually, you get this. Its internal probability distribution starts to look exactly like the real world. The mystery is solved. So to bring it all home, here's the big takeaway. RBMs are these powerful models that can find hidden features in data, the pets that explain the people. And since calculating every possibility is just impossible, we train them using this really clever hack called Contrastive Divergence, which is all about constantly comparing reality to the model's own short dream. If this look into the hidden layers of AI helped things click for you, please do me a huge favor and hit that like button, share this with someone you know, and definitely subscribe to the Think Information, Think AI, Think Success channel for more deep dives into models just like this. And this leaves us with a final, fascinating thought. Our neighborhood mystery was pretty simple, but this exact same technique can be applied to data that is way, way more complex, from finding hidden trends in the stock market to spotting features in medical images. It really makes you wonder, what other invisible forces, what other hidden patterns in the data all around us are just waiting for a model like this to bring them into the light? Thanks for watching.